so I have to introduce some terminology. So so what I'm doing right now is I'm clearing up, so in the book, in the induction chapter, they'll say they gave you this principle of weak induction, and then they gave you this principle of strong induction. And they just said, okay, they're theorems and they're the same, okay? And so last time I told you that I showed essentially how the weak induction and strong induction were the same, provided that you had the symbol less than or equal to, and you could make sense of that symbol, right? And I said that I cheated, okay? So I think in order to remedy this and give you guys an explanation, a full explanation of why weak induction and strong induction are the same, I need to first introduce some terminology, right? So that I can show you this piano arithmetic, which is like a longer version of the Dedekind piano axioms, those original axioms that I gave you for the natural numbers, and that allow us to talk about the inequality. So today I'm going to introduce vocabulary for talking about these things. Okay, so so let me start, and with that I'm going to give the title. So it's about today is about signatures, structures, signatures, formulas, structures, theories, and models. And so this is kind of how we build up logic formally. Okay? And I'm using this because I want to talk about the difference between having a less than or equal to sign with the axioms of the natural numbers and not having a less than or equal to sign, and what this difference is technically. Okay? So, so a signature, so let's start with signatures. Okay? Okay. So, and I'm just going to go through this list of things. Okay, so a signature is a set of operation symbols, operation, relation, and constant symbols, Okay, so for example, they could be a multiplication here, or they could be like an inequality, or they could be like the group identity, or the identity for multiplication in a ring. So it's the collection of things that we use to build the formulas for the formulas that we're going to use, the mathematical formulas that we're going to use. So these are the collection of things we use to make mathematical formulas. Okay, not including the quantifiers. So the quantifiers, parentheses, and equal signs will be given. So let me give you some examples. So to talk about groups, we use the signature and I'm going to call this sigma, and then I'm going to use the underlying thing here. So sometimes this is called a sort, but I'm going to include this in here. So groups, we just have two symbols that we really use. We have a multiplication symbol, so that's our binary operation, and then we have our constant symbol. There's no relations in this one. So this thing here is our operation. This is the binary operation, our symbol for the binary operation. And this is the symbol. This is the symbol for the identity. So this is an operation symbol, and this is a constant symbol. Okay, and then this is just an underlying set or sort. Okay, so it's like a symbol we use for the thing. So let me give you another example. To talk about rings, we use the following. This signature. This is the Greek letter sigma, by the way. So we use the signature where we have this ring, the ring sort, and then we have an operation of addition. We have the operation of multiplication. There's no relation symbols. There's nothing like less than or equal to. We have the free relation symbol equal sign, but we don't write that one down, right? And then we have 0 and 1. Okay, so here are our function symbols, our operation symbols, and then here are our constant symbols. All right. So to talk about the natural numbers, so in the Dedekind piano, for the Dedekind piano, we used this natural numbers here, and then we had this function. This was our successor function, and then we had either 1 or 0, and so this thing here was our starting place. So this is the constant symbol, which is our starting point, right? And then this was the successor function. Okay, and so this was a function which takes the natural number and it returns a natural number, and the idea was that it would return n plus 1. But right now, we're not assigning them meaning, we're just making symbols for them. Okay? So these were the signatures. Okay? So let me talk about formulas now. So for formulas, okay, so for formulas, so from the signature, we produce formulas. Okay? And the formulas are, okay, so let me just give you the idea. So the signature we have formulas here. Okay? So in the signature, right, we could have something like the group with the group multiplication and then the identity axiom. And then from that, we could produce formulas. So formulas, they have variables in them for all x, y. Let me just start one. This is like x is equal to y times z. So these are with free variables. This is an example of one. Or you could have something like, for all x, there exists a y such that x times y is equal to e. Or you could have something like, that doesn't necessarily have to be true. For all x and all y, x times y is equal to y times e. Okay, so these are some examples of formulas that we have. They don't necessarily have to be true for groups or anything. They're just things, right? Okay, and so like I said, we're allowed to use equal signs and parentheses how we want. So I'm not going to include those in the signature of the things that we're allowed to say. But the basic idea, right, is that to build formulas, how formulas are built. So how are built, right? So you start with basic formulas, basic or atomic formulas, right? So these come from basic inequalities, so relation symbols. By themselves, like r of x, y, or x is equal to y, right? Or function symbols. With, formulas with basic functions, with function symbols. So you could have something like so here f of x is equal to y, or x times y is equal to z. So here, I should mention that r, f times are assumed, or say symbols in the signature. Okay, so we could start with like a basic relationship, right? If we have a relation in our signature, we can start with a basic formula like this, right? Okay, and then you go from this, from basic ones to more complicated ones. Right? So by taking basic ones, and then you can quantify free variables, or you can apply connectives. So connectives are the things like and, or, and not. So if I have a basic one, like this one or things like this, right? I could take this and this, or I could take this and this, or this or this, or not this and this. Or I could say, for all x, y, y times, for all x, x times y is equal to z. Things like that, okay? So I could, these things have free variables here. These are all with free variables. Free variables. Okay, so to build up all the possible formula, I start with these basic things, and then I apply connectives and quantifiers to get all other formula. And so I generate all my formulas in this way. Okay? Okay, so let me make a small distinction here. So sometimes we allow formulas which are first order and some formulas which are second order. Okay, so let me just clarify what this means, right? So, okay, so sometimes our formulas, we allow ourselves to quantify over subsets of the universe or predicates. Okay, so my claim is that quantifying over subsets and quantifying over predicates are the same thing. It's the same thing. Are the same. Okay, so let me give a proof of this. So if we quantify over predicates, so if we're given a predicate, so this is just going to be like an informal proof, right? So given a predicate P, right, we can do P of x. We can form the set of x such that P of x. Okay, so from a predicate, you can create a subset. Okay, subset of the universe. Okay, similarly, if you're given a subset, so if you have a subset S of the universe, we can go this way to get a predicate. X is an element of S. Right, so this is a predicate formed from the subset. Okay, so these are really the same thing. Okay, do you guys see what I mean by this now, that the quantifying over predicates and quantifying over subsets are the same thing? And let me give you an example of where we quantified over predicates or subsets. So an example of a statement where we quantified over subsets. Okay, so in in the Dedekind-Peano axioms, Dedekind-Peano, right? We had this induction axiom, right? It said that for all S, a subset of the natural numbers. So this is a quantifier over subsets. You see? So this is for all subsets of the natural numbers. If 1 was an element of S, and for all n in the natural numbers, if n was an S, this implied, and then we had the successor function, so S of n was an NS, then these two things, these two things implied that the following was true, that S was equal to the natural numbers. Okay, so here was this induction axiom, right? And the induction axiom said for all subsets, blah, blah, blah. Right? And I mentioned that we could have formulated it as for all, propositions, if P of 1 is true, and P of n implies P of n plus 1. And so, let me tell you that there's two, this is kind of a poor choice of letters here. This is a lowercase s. This lowercase s is really represents lowercase s of n is n plus 1. Right? It's the successor function. But I'm trying to be careful about what symbols I use today. Okay? So we used n plus 1 before. Okay? This is how we're supposed to think about it. Okay? So this was the axiom of induction. Okay? And so formulas. Okay, so now, so let me give you some terminology. Okay, so formulas which don't quantify over subsets, equivalently predicates, are called first order. Okay, and formulas which quantify over subsets of the universe are called second order. In the second statement, I didn't say subsets of the universe, quantify over subsets of the universe, right? And I could have written equivalently predicates. If you quantify over predicates, it's also second order. Okay, but you can always convert between the two very easily. Okay, and using this thing. So if you have a predicate, you form the set of x such that P of x is true. Okay? And if you have a subset, you form the predicate that X is an element of S. Okay. So yeah. So okay. So those are second order things. So so we have a notion of first order and second order formulas. Formulas are built from the signatures, right? And sometimes we allow for them to quantify over subsets of the universe. Okay. With this element symbol. Okay. And like we did for the Dedekind piano axioms. So we call that a second order thing, a second order formula. Okay? Okay, so there's just a lot of words. Okay. All right, so we've talked about signatures. Signatures were the symbols we're allowed to use. From the signatures, we get the formulas. The formulas are either first order or second order. Okay, and they're just things that we can say. Okay, so now let me just say something about structures. Okay, structures. Okay. So structures. So a structure for a signature. So a structure for a signature sigma is a set M together with actual relations, operations, and constants, that allow us to give meaning to formulas. To give meaning to bounded formulas. So this means that when we have a structure, right, we get to interpret the symbols. So this notion is due to Tarski, by the way. Okay. So we're allowed to interpret the symbols, right, to give meaning to the formulas. Okay, so let me give you some examples. Okay, so here's an example. Let's do the examples here. And they don't necessarily need to be so. So let me give you an example. The formulas don't necessarily need to be true, okay? So for the signature, we use to talk about groups so this is the signature sigma. We'll call it G. We have our multiplication symbol. Then we have our identity here. The following are structures for sigma. Okay, so we'll do the natural numbers, and then we'll do it with multiplication. And we'll do 5. Okay? We could do the natural numbers with addition, and we could do, say, 5 as well. Or we could do, I don't know, pick another 100, I don't know, 10. That's fine, right? Or we could do z. Here, we could do z plus and 0. Okay, so these are all structures here. Okay, these ones are. This is not actually a group, right? It just means that I can take a formula. So, for example, with the first structure here, the formula in the first example, the formula here, for all x, there exists a y such that x times y is equal to e, right, becomes, okay, so an actual thing. X dotted with y is equal to 5, right? So this thing is false, right? No, this is false. Right? We just care that it returns, that we have something that allows us to return a true or false value, right? The ability to return, or false. And so this is a bounded formula here. So notice that there's no free variables. X is quantified and y is quantified. And so we only care about like whether or not this formula makes sense, right? Okay, so, and this is a structure for this signature. Do you guys make sense? So it doesn't matter if we do multiplication. We can interpret this operation as or addition as well, or multiplication. This doesn't need to be 1. The identity doesn't need to be the identity. It's just something. This is an example here where it actually happens to be a group, right? But we don't really care. We're not really concerned about groups right now. We're just concerned about structures, okay? So that's what a structure is. Yeah. Oh, okay. Okay. So now let me talk about theories. Okay, so we've talked about signatures. From signatures come formulas. Okay, and structures are things where we can interpret the formulas given the signature. Okay, so theories. What's a theory? So a theory with signature sigma is a collection, is just a set of bounded formulas. It doesn't matter what the formulas are. I just take any collection of formulas, and that makes a theory. It could be the stupidest theory in the world, right? But it's a theory. That's what we call it. Okay? So for example, for groups, our theory, we have our signature. The signature, here's sigma, and this is going to be, so this was, so we have the sort here, then we have the multiplication, and then we have the identity. We have the signature this with the theory being so T is the set of A, B, C where A is equal to, here, A is equal to the following thing, is that for all x, x times E is equal to x. Okay? B is the formula for all x, there exists a y such that x times y is equal to E. So that there's a right inverse. And C, and I could strengthen this if I wanted to. I could add that not only there's a left x, that this inverse is the right inverse, but it's also the left inverse as well. So I could add that as well if I wanted to, right? C could be for all x, all y, and all z, that x times y times z is equal to x times y times z. Okay? So this was the formula for this is a theory of groups. It's this collection of we could just say a subset of these things. Okay, and so a subset of formula. Okay, so that's what it is. Does that make sense? So note that all these things are bounded, and all these formulas here, they're first order. So this is a first order theory of groups. Okay, there's no statement here about that quantifies over sets. The Dedekind piano axioms, on the other hand, they did quantify over subsets. It had that induction axiom that said, well, for every proposition, if you have the first thing and then this idea where you can go p of n to p of n plus 1, then that implies for all n p of n. That's a second order theory, okay? Because one of the formulas in there is a second order thing. Okay. Okay, so let me recap again. Okay, signatures. Those are the symbols that you use, right, to make up your formulas, okay? Your formulas are built from the atomic things, and we use connectives and quantifiers to build up from there. Okay? Then after that, they could be first order or second order. Second order ones are where you quantify over sets. Okay? Then we had structures. Structures were sets with relations and operations and constants that allow us to interpret the formulas. So for example, if we had the theory of groups, we had the signature for groups. And we had a set. We could assign the multiplication meaning for that particular set, and that would be a structure for the theory of groups, or for the signature of groups. All right. Then we had theories. Theories were just a subset of formulas. It had nothing to do with structures or anything. It's just a collection of formulas that you can make. Okay. Now I'm going to tie theories and structures together. Okay, so these are called models. Okay, so a model, so fix a signature, sigma. So a model, and let T be a theory. Theory with formulas for the signature sigma. Okay? So a model of T is a structure for sigma where every formula in T, is true in this structure. Okay, so there's a notation that we use for this. So this is a kind of a cool logic notation. So we say that M proves T. So it's not just M, right? So when I say as a structure M, okay? So when I say M really comes with all the data that comes in the signature. So if your signature has a binary operation, your M has a binary operation. If your signature has a constant, M has a special constant in it. Okay? If your signature has a function or not, like a relation here, like a less than or equal to sign, M comes with a relation or less than or equal to sign. Okay? And so this notation is that M is a model of T. Okay. So that's what we call what am I saying? So this is what a model is. So for example, for the theory of groups, if T is the theory of groups, then these examples here, this thing here, we had the natural numbers, with the natural numbers, what did I say, times and 5 is not a model of t, right? But this thing, z plus in 0 is a model of t. Okay, is the model for, so this is an actual group, i.e. z with the plus operation and e being 0 is a group. So any model for the theory of groups is what we call a group. Okay? That's all that I'm saying. Okay, so now let me recap. Let's recap one more time. Okay, so we started with signatures. Okay? Signatures are the collection of symbols that we're allowed to make our formulas from. So it's like plus, times, constant symbols, whatever. Our formulas are built from atomic formulas. From there, we build more complicated formulas by using connectives and quantifiers. All right. Sometimes we allow quantification over subsets. Those are called second order formulas. If we don't do that, then they're just called first order. All right. So given a signature, we have a notion of a structure. A structure is just a set with some operations which allows us to interpret each of the formulas. The formulas, and it returns true or false. Okay? It doesn't matter, that they satisfy some axioms. It just means that we can assign meaning to the formulas. Okay? So a theory is just a collection of formulas, and a model is a structure where all the formulas in the theory are true. Okay? That's it. So there's a lot of words. Okay? And so in the homework, I'm just going to have you guys, I'm going to give you guys some examples, and you guys are going to say, is it a structure? Is it a model? Right? Things like that. Yeah?
So you could have structures that are, so structures are true or false. Right?
Yeah. So you can take a formula, and then you kind of plug in the model into the formula, and it'll say, OK, this, like for a bounded formula, right? So this is a proposition, right? It'll return true or false. Yeah.
So you can have the structure and a model of something that abides by groups, but until you imply the theory of groups, it doesn't. I don't want to say it doesn't matter, but
yeah. I mean, so for example, every model is a structure, right? And so there's certain things which I can check so if it makes sense for me to check the axioms of groups against this thing, so then that's a structure, right, for that signature, right? It makes sense that I can okay, does it even parse that this thing could be a group, right? Does it have a binary operation? Does it have something that you called the identity, right? Well, then that's a structure and you can check it, and the axioms will fail, right? Or if it is a model, then the axioms will be true. Does that make sense?
Yeah.
I don't know if I clarified what you're saying, but yeah. Yeah?
Can you just repeat again what's the difference between theory and a structure?
Okay, yeah. So a structure, right? So a theory and a structure are different, right? So a theory is just a collection of formulas that you build, right? The difference between a structure and a model is that, models, so for a structure to be a model of a theory, you need every single one of the formulas in the theory to be true when you investigate it for that particular structure. So a structure is promoted to the rank of model if it verifies the axioms. So once you verify the axioms, then it becomes a model, right? So for example, in the theory of groups, if you have an actual group, that's a model for the theory of groups, right?
So if it's true, if any structure that is true becomes a model.
Yeah, exactly. If you have a structure and then you check your formulas and it turns out to be true, then it becomes a model. Yeah. It passes and you get to call it a model. So it's just a lot of words, right? But these words allow me to say things more succinctly. Like the reason why I introduced all these words is in order to talk about the difference between the Dedekind piano axioms and piano arithmetic. And the key difference is the signature, okay? And some people, and the way that you can formulate the axiom of induction, Okay? So piano arithmetic is the famous one, the famous set of axioms that the incompleteness theorem are about. Okay? And so in order to talk about that precisely, I wanted to introduce some of this terminology. Okay? And so, and in the background of piano arithmetic, which are these axioms for the natural numbers, which have a larger signature. So originally, our signature for the Dedekind piano axioms just had the successor function and a constant element, right? And now, for piano arithmetic, we're going to have a successor function, a constant element, but we're also going to have plus and times. Okay? And so plus and times allow us to say more. In particular, talk about the ordering of the natural numbers that we needed to in order to say that strong induction and weak induction were the same. Because remember, I was using the less than or equal to sign everywhere, but I didn't, I told you I was cheating, right? And that cheating was because I was using something that wasn't in the signature of the theory, okay? So technically, that's what was going on. So what time does this end? 7 minutes, okay? So so what I'm going to do is I'm going to write down the axioms for piano arithmetic, and then next time I'm going to explain how the Dedekind piano axioms and piano arithmetic are different. And so I guess next time will mean, generalized next time because we have review, right? And then so we have a review next class, and then on Monday you don't have class, and then on Wednesday we have the test, okay? So you'll have to hold on to this kind of hard for next time. And I'll do a little recap before, so I guess it'll be next Friday, right? So it'll be like a little while before we actually get into this. Yeah. Abby? Oh.
So for the exam, what chapters are
We're just not induction, so up to chapter 2. Yeah. And so, before I write these things down, so I'm gonna, I started writing the test, right? I need to throw out some questions, and so I'll make the ones that I throw out available to you guys, right? So you can kind of see what type of things I was thinking about. And then I found some practice exams from another old Math 52 class that I'll make available to you guys. Okay? Yeah?
How group-centric is this exam going to be?
I mean, not very. It's part of the class, right? And the reason I gave you guys multiple group questions because, on the homework is because, you guys didn't do so well the first time, so I wanted to make sure that you did it. So, I mean, if you go do the handouts and the homeworks, they should be sufficient, yeah. 1 and 2. Yeah. Chapter 1 and 2. The book is Lakin's, so it was the one on the course description originally, or the syllabus. Yeah, we can talk about this after if you want. Okay, so let me write down these axioms for piano arithmetic, and then if you have more questions about the test, you can come ask me after class. Okay. All right. Okay, so for piano arithmetic, okay. Okay, so here are the axioms. So piano arithmetic is a theory with the signature okay. So we have. So I'm going to do this. So I'm going to include 0. Okay. And then we have this guy. So this is the successor function. Right? And then we're going to have two new operations, right? Plus and times. And then we also have 2 constant symbols. Or no, 1 constant symbol. We're just going to use 0. So this will be the starting point, and it'll serve the purpose of the identity for addition. Okay? So it has this signature, and it satisfies theory contains the following formulas. Okay, and I'm going to list some of them that are actually contained in the signature. So as you guys might remember that I wrote down 3 axioms for groups, right, in today, right? But you had to check 4, right? Really, the 4th axiom is part of the structure, okay? So the 4th axiom, that thing about the closure, right? That's why I didn't include it the first time, because it's actually part of the structure, okay? But it is something that you need to check. So some people you can call it an axiom if you want, but technically it's part of the structure. Okay. Anyway, I'm going to write down what they are. So there's going to be 8 axioms. 0, 1, 2, 3, 4, 5, 6, 7. Okay, and then there's this induction axiom, which will be over here. 8. Okay, so the 0th, so these 2 axioms are not really axioms, but they're part of the signature. So if n is in here, this implies Sn is an element of here. So these things are really part of the structure. So you could omit them once I specified the signature. Technically, you don't have to write those down. Okay? Now that we have this language of signatures. Okay? The verbiage here. But we do have to write down these. If this is true, then n is equal to m, right? We already wrote that one down. And then we had that for all n, Sn is not equal to 0. So these ones here, let me just say this here. So these were the Dedekind piano things. Dedekind piano. And now we're add these new axioms here, which allow us to talk about multiplication. And they're pretty innocuous, right? N plus 0 is n for all n, right? The other one says that if you add n and the successor of m, that's the successor of n plus m. So it tells you how successor behaves with respect to addition. And n times 0 is equal to 0. And that n times the successor of m is equal to n times m times n. Okay, and that's like the distributive rule. Okay? So these are the axioms here. And then plus the 8th axiom is an axiom of induction. Then there's 2 ways to do this, right? There's a first order way and there's a second order way. The first order way is that you could actually add an infinite number of axioms, right? Instead of adding predicates. And you add it for all formulas with one single free variable, right? And the other way to do it is with predicates. So these things here, let me just say this here. So this is for how plus and times behave. And then I'm not going to specify this here. Maybe we can talk about this when we want to be more precise. But I'm just going to say there's an axiom of an induction, and that there's a first order way of doing this, and there's a second order way of doing this. It's your choice, kind of. Okay? Finally, the point of this is that so what's one of the big points is that, so in this theory, we can define the following. X is less than y. Okay? So this is what we really wanted to get at, right? If and only if there exists some z such that S of z plus x is equal to y. Okay? So you define, this is by definition, we define the inequality to be this way. And this now is a formula here, right? This is something that we can define using our signature and our stuff here, okay? So this allows us to define the inequality, okay? And so I'll say a little bit more about this next class.